So thank you very much. Yeah, my name is Attila Galsa from the Department of Geophysics at Eötvös Loránd University, as you did mentioned in the introduction. Thank you. And I would like to talk about the dynamic interaction of different forces which drive the groundwater flow, at least in our numerical models. So we, together with my colleagues, with my co-authors, published this research last year in the Journal of Hydrology and Earth System Sciences. So first, I'm going to talk about three forces which can control the groundwater flow in our numerical model, and also about our motivation, our intention behind the research. Then I'm going to present our numerical model, including both the mathematical and the numerical parts. And third, we will discuss the numerical results obtained from the synthetic simulations and also a bit more realistic hydrogeological situation. And finally, I will close my presentation with a brief summary and conclusions. So, the evergreen question has come up in numerous scientific discussions. What drives the groundwater flow? Which one is the most dominant force? So some has stated that the topography of the groundwater flow the topography of the water table governs the groundwater flow, inducing fluid motion from the recharge zone towards the discharge zone. But others who studied deep geothermal reservoirs argued that no, the free thermal convection must be the most important force. Still others who believe that the total dissolved solid content is what primarily influences the groundwater flow, for example, near coastlines. So the free haline buoyancy must be the most important effect. So at that point, we decided to incorporate these three forces into our model, which is called topothermohaline model. So let the system itself determine which force is important and which force is negligible. Okay, only one slide about the physical background of topothermohaline convection. So the Darcy flux, which is denoted by Q, can be calculated from solving the mass conservation on the Darcy's law, and the Darcy flux influences the temperature, the solute concentration, and the water age through the advection terms of the heat transport, the mass transport, and the age transport equations. So the computed temperature and salt concentration varies the water density, which modifies the Darcy flux again. Thus, the whole partial differential equation system is coupled in our model with the unknowns of the Darcy flux, the temperature, the salt concentration, the water age, and the pressure. So I note that in our model, the molecular diffusion coefficient is temperature dependent. And now on our synthetic numerical model, so the model length was 40 kilometers with a thickness of 5 kilometers. And the boundary conditions for the flow was no flow on the vertical boundaries and also along the bottom of the model domain. And the topography-driven groundwater flow was controlled by a simple cosine water table with an amplitude of 50 meters. As a consequence, the water flows from right to left. So for the temperature, insulating vertical boundaries, and insulating vertical boundaries, and 90 milliwatt per square meter was prescribed along the bottom of the model domain with a constant value of temperature on the surface. For the salt concentration, so no flux along the side walls, and constant values of salt concentration was applied along the horizontal boundaries. and for the for the water age, so no flux along the side walls and along the bottom of the model domain, and we applied an open boundary condition on the surface. So during the parameter study, we will write 3 model parameters to investigate the behavior of the topothermohaline system. So first, we will write the amplitude of the water table influencing directly the Darcy flux in the model domain. Second, the bottom heat flux, which affects the temperature of the model domain. And third, the salt concentration along the bottom of the model domain, which influences the topothermohaline convection through the salt concentration. So first, I would like to present the quasi-stationary solution of the magnitude of the Darcy flux, the temperature, the salt concentration, the salinity zones, and the water age in our reference model, in our base model, with a water table amplitude of 50 meters, with a bottom heat flux of 90 milliwatt per square meter, and a salt concentration which was fixed at the bottom of the model domain as 70 gram per liter. By the way, the salinity zones were defined after damming. For example, where the concentration was below 1 gram per liter, it is considered fresh water. So we can see that the recharge zone and the central parts of the model domain, of the synthetic model domain, is controlled by topography-driven forced convection, sweeping the heat, the saline and old waters out of the system. So as a consequence, these parts are characterized by cold, fresh, and young waters. Plumes or hot upwellings are emerging, and they are drifting towards the discharge zone due to the topography-driven forced convection. On the other side, beneath the discharge zone, a so-called thermohaline dome forms with vivid thermohaline convection, and it is characterized by hot water, high salinity, and high water age. And now, let's see the qualitative effect of the water table amplitude. So when the water table amplitude H was decreased from 50 meters in the base model to 20 meters, the thermohaline convection occupies most of the basin and forms a thermohaline layer with high temperature, salinity, and extremely high water age. The topography-driven groundwater flow dominates only a thin near-surface layer beneath the recharge zone. However, when the water table amplitude is as high as 200 meters, the topography-driven forced convection is strong enough to sweep the heat, the saline water, and the old waters out of the system, and the thermohaline dome shrinks into the deepest parts of the basin beneath the discharge zone, leading to an almost stationary solution, which is very, very similar to the purely topography-driven groundwater flow model or problem. So using control parameters, we are able to quantify the effect of the water table amplitude. For example, when H, that is the water table amplitude, is less than 20 meters, this is the thermohaline layer mode, the relative size of the saline water zone exceeds 90% in the synthetic model domain. But if the water table amplitude is increased, the transitional thermohaline dome mode shifts to the topography-driven groundwater flow mode, where the basin is filled with fresh water. So in the thermohaline layer mode, the Darcy flux, the temperature, the solute concentration, and the water age average for the total model domain is characterized by the saline water zone. This is the orange curve. So it is characterized by the saline water zone. However, if the water table amplitude is increased, the flow in the basin speeds up, becomes more intense, leading to reduced temperature, reduced salt concentration, and decreased water age by almost 3 orders of magnitude. And now let's see how the bottom heat flux influences the operation of the topothermohaline convection through the temperature. So when the bottom heat flux is as low as 50 milliwatt per square meter, the thermal buoyancy is reduced, which weakens the thermohaline dome. That's why the size of the thermohaline dome decreases, and the thermohaline convection becomes less intense. On the other hand, when the bottom heat flux is as high as 120 milliwatt per square meter, the thermal upwellings are so strong that they are able to destroy, to disintegrate the thermohaline dome beneath the discharge zone. Okay, and they are drifting toward the discharge zone due to topography-driven forced convection. So quantitatively, for example, the size of the saline water zone, this is the size of the thermohaline dome has a maximum in the base model. So when the bottom heat flux is equal to 90 milliwatt per square meter. But when decreasing the bottom heat flux weakens the thermal buoyancy, that's why the size of the thermohaline dome decreases together with the temperature. This is the black curve, the temperature average for the total model domain. On the other hand, when the bottom heat flux is increased, the thermal buoyancy becomes so strong, the thermal upwellings makes so strong that they are able to destroy the thermohaline dome. That's why the size of the saline water zone decreases together with the temperature. So what does it mean? So high bottom heat flux paradoxically leads to reduced temperature. Why? Because the thermal upwellings are so intense that they are able to advect heat out of the system. I think it is worth noting that the saline water zone has the maximum temperature, has the maximum water age, of course the maximum concentration, and the flow is the slowest in the saline water zone compared to the freshwater zone, which is characterized by cold, young, fresh waters and with fast groundwater flow. And finally, let's see the qualitative effect of the bottom solute concentration. So when the solute concentration along the bottom of the model domain is only 10 grams per liter, the role of haline buoyancy is reduced. So the role of the haline buoyancy can be neglected, and the synthetic basin is governed by the topography-driven forced convection, which is perturbed by hot ascending upwellings. On the other hand, when the bottom solute concentration is as high as 200 grams per liter, due to, for example, an evaporite layer below the synthetic basin, so the negative haline buoyancy is so strong that the thermal convection, the thermohaline convection, the groundwater flow is reduced, is retained. That's why on the beneath the discharge zone, a strong and multi-layered thermohaline dome forms with extremely high temperature, salt concentration, and water age. All this in numbers. So when the bottom solute concentration increases, the relative size of the freshwater zone decreases from 100% to approximately 50%. Parallel to this, the size of the brackish water zone, then the saline water zone, then the brine water zone increases. So, increasing the bottom solute concentration reduces the groundwater flow. That's why the Darcy flux averaged for the total domain, this is the black curve, decreases, leading to increased temperature, increased water age, and also increased solute concentration. So I note during in our parameter test, the bottom solute concentration was increased from 2 gram per liter to 200 gram per liter, so by 2 orders of magnitude. Meanwhile, the concentration average for the total domain increased by 3 orders of magnitude in the coupled topothermohaline model. And now we can turn on the demonstration area. So the operation of the topothermohaline model was demonstrated along a 2D hydrogeological section crossing Buda thermal karst system in west-east direction. In the right figure, you can see the topography and the geological structure along the section, which is divided into 2 parts by the river Danube, into the western part and into the eastern part. The water table elevation was measured in wells, and the geological formations were grouped into 11 hydrostratigraphic units, which were characterized by parameters based on measurements and the literature. So the model parameters of the 11 hydrostratigraphic units are tabled here. From the point of view of groundwater flow, the most important parameter might be the hydraulic conductivity, which were estimated mainly from well tests. So for the sake of simplicity, the main aquifer of the karst system is the Triassic carbonate karstic carbonate, which is in unconfined form in the western part of the system, but it is confined by the Oligocene clayey aquitard in the eastern part of the karst system. So the main difference, I think this is the main difference between the 2 parts of the karst system. The western part is unconfined, the eastern is confined. So the simulations were started from conductive temperature distribution, and the units were saturated by saline water with a salt concentration of 35 gram per liter, because these sentences were deposited in marine environment. The initial water age was set to 0. So we will see the evolution of the Buda thermal karst system, including the Darcy flux magnitude, the temperature, the salt concentration, the salinity zones, and the normalized age for the first 500,000 years. So only 10,000 years is enough for precipitation to infiltrate through the unconfined karstic aquifer, and it is saturated by cold, fresh, and young waters. On the other side, the confined eastern aquifer is characterized by hot, saline, and aged waters. Meanwhile, hot upwellings are emerging from the deepest part of the karst system, and they are drifting together with the topography-driven forced convection. The boundary between the 2 types of waters are continuously but a slowing rate shifting, migrating eastwards. Okay, so now we are over the first 200 kilo year, and we can jump into the final snapshot. So after 1 million year, it can be established based on the Darcy flux streamline pattern that the unconfined part and the western part of the confined karstic aquifer is controlled by topography-driven groundwater flow, and these parts are saturated by cold, fresh and young waters. On the other side, in the eastern confined aquifers or reservoirs, thermohaline convection forms with high temperature, high salt concentration, with saline and aged waters. Okay, so the two types of waters are mixing in the western part of the confined aquifers, and the compositionally and thermally mixed waters facilitates karstification and moves westwards directly beneath the clay Oligocene aquitars and reaches near the line of the river Danube at the margin of the unconfined and the confined karst system. And now about the time series. So the time series of the relative area, the Darcy flux, the temperature, the salt concentration, and the water age of different salinity zones illustrate that the system reaches its quasi-stationary state after about 300 kiloyear, apart from the saline water zone where the flow is the slowest. For example, the relative size of the saline water zone decreases in time. However, the flow increases in the saline water zone slightly. The periodic behavior on the time series of freshwater zone and brackish water zone suggests that thermal or thermohaline convection might occur in the deepest part of the karstic aquifer. And I can repeat that the saline water zone has the highest temperature, the highest water age, of course the highest concentration, and the slow is the slowest in the saline water zone. And okay, and one of our reviewers noted that in our model, the molecular diffusion coefficient is temperature dependent. The water density is pressure, temperature, and concentration dependent, but the temperature dependence of the water viscosity was neglected. Why? So we incorporated into our model the pressure, the temperature, and concentration dependent viscosity, and repeated our simulation along the BTK, along the Buda-Therma karst system. We experienced that the main conclusions remained unchanged. The unconfined and the western part of the confined aquifers are controlled by topography-driven forced convection, and these parts are saturated by cold, fresh, and young waters. On the other side, in the eastern confined aquifers, thermohaline convection forms with high temperature, rather brackish, and older waters. But the main difference between the two solutions, it can be said that the water viscosity depends primarily on the temperature. That's why the water viscosity decreases in the hot reservoir, which facilitates the heat transport, the solute transport, and the H transport as well, leading to a geothermal reservoir with lesser extent, lower salt concentration, and younger waters. in my opinion, it seems a bit more realistic solution than the constant viscosity solution. And now we can turn on the brief summary. I'm not going to read all of sentences, all of statements. So based on our synthetic simulations, so when the water table amplitude is decreased, the thermohaline convection dominates the whole basin, leading to high temperature, salt concentration, water age, and slow flow. However, when the water table amplitude is increased, the topography-driven groundwater flow dominates the whole system, resulting in low temperature, salt concentration, water age, and fast flow. When the bottom heat flux is increased, the thermal convection is so intense that it is able to disintegrate the thermohaline dome beneath the discharge zone, resulting in low temperature, salt concentration, and water age. But when the bottom solute concentration is increased, we saw that a multi-layered thermohaline dome formed with high temperature, salt concentration, and water age, and with sluggish groundwater flow. And now the summary concerning the hydrogeological section, and I would like to focus only on the last sentence. So, from a geothermal perspective, the eastern parts of the Buddha thermal karst system are the most promising, particularly those located farther away from the unconfined areas, so the eastern part. And the take-home message. So, topothermohaline convection in porous medium describes the dynamic interaction of the topography-driven forced convection, the free thermal convection, and the free but negative haline convection. So in such a complex model, in such a complex system, the quantitative solution can sometimes be predicted. For example, it seems to be logical when increasing water table amplitude sweeps the heat, solutes, and aged water out of the system, leading to low temperature, salt concentration, and water age. But sometimes the solution cannot be predicted even qualitatively. For example, higher bottom heat flux paradoxically reduces the average temperature, as we saw in the graphs. In addition, the quantitative impact of certain parameters can only be determined through precise and systematic simulations. And finally, my last advice, it is advisable to develop a model that incorporates all three effects, which helps mitigate the numerical modelers like me, the subjective bias. So thank you very much for your kind attention.